Variations on equilibrium, looking at how Kc changes with equation. I can change the balanced chemical equation of any particular reaction by manipulating it in various ways. Changing that balanced chemical equation is going to change the reaction. In a similar fashion to Hess's law, I can change my equation several ways. I can reverse the reaction, and if I do this, I'm going to invert my K value. I can multiply my reaction by a factor of n. So for instance, I can multiply all of my stoichiometric coefficients by 2. If I multiply by a factor of n, my value of K is going to be raised to the nth power. I can also split reactions into multiple steps, like I can in Hess's law. In doing so, the K value overall is going to be equal to the K value for each step, all multiplied together. The reverse equation flips the expression overall. If I take 2SO2 plus O2 producing 2SO3, flipping that around to make 2SO3 producing 2SO2 plus O2, you'll notice obviously that the products have become the reactants and the reactants the products. What I have to do to my equilibrium expression then is to flip it upside down. I have to invert it. So my initial Kc with SO3 to the second power on top, O2 on bottom and SO2 squared on bottom, now becomes Kc prime of O2 on top, SO2 squared on top, and SO3 squared on bottom. Obviously, if I've inverted the entire expression, I've essentially taken the reciprocal of the Kc value numerically, because all of my numbers are now on the opposite side of the divisor line. So the value of the Kc prime should be expected to be the value of the Kc against 1, so 1 over Kc. If I multiply my equation by a value of n, I'll raise the Kc value to the nth power. So if I take my equation and I multiply it by 1/2, I'll get, instead of 2SO2, I'll get SO2 plus 1/2 O2, producing 1 SO3 instead of 2. What this does then is produces a Kc double prime of SO3 rather than SO3 squared divided by O2, now raised to the 1/2 power, times SO2 raised to the 1 power. Doing this numerically gives me a Kc value for Kc double prime equal to Kc raised to the nth power. In other words, Kc raised to the 1/2 power in this case. If I have a multi-step process such that A reversibly produces 2B with a K1 value of B squared over A, and 2B producing C with a K2 value of C over B squared, I can find that Kc overall for C against A, for a reaction of A producing C, is going to have C over A. The Kc value overall numerically is going to be K1 times K2, because if I multiply K1 by K2, you'll notice that B squared cancels out because it's the numerator of the first and the denominator of the second, and that leaves me with the concentration of C over the concentration of A. In addition to expressing the K in terms of concentration, the Kc that we've been mentioning, we can also express K in terms of pressure. We know that PV equals nRT. If I divide both sides by V, I get nRT over V, and we know that N moles over V volume is molarity. So we can express pressure as being molarity times RT. If P then is proportional to concentration, we can create a similar expression in terms of pressure as we did with concentration. For our Haber process of ammonia formed from nitrogen and hydrogen, the Kp here would be the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 to the third. At 500 degrees Celsius, the Kp value for this is 7.11 times 10 to the negative 5. If pressure is equal to molarity times RT, then molarity is equal to pressure divided by RT. I can substitute this into my Kp expression such that I have pressure over RT plugged in for each of the values. So I get pressure of NH3 over RT squared divided by pressure of N2 over RT times pressure of H2 over RT cubed. I can factor out 1 over RT from each of these, and in doing so I'll get the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 to the third, all multiplied by 1 over RT raised to the second power divided by 1 over RT raised to the fourth power, because when I multiply two things with exponents, the exponents will add together. So my 1 from the nitrogen and my 3 from the hydrogen added to make 4. I can reduce the RT ratios and substitute Kp such that we know Kc is going to be equal to P NH3 squared over Pn2 times pH2 to the third times 1 over RT squared divided by 1 over RT to the fourth. When we divide exponents, like we do with the RTs here, our exponents subtract. 2 minus 4 gives us a value of negative 2. So that becomes 1 over RT to the negative 2. Canceling the negative exponent by flipping things over the divisor line, I get RT squared. If I plug in Kp for the pressure expression P NH3 squared divided by Pn2 times pH2 to the third, I get Kc equals Kp RT squared. If I flip that, pressure becomes Kc RT to the negative 2. If Kc is Kp RT squared and Kp is Kc RT to the negative 2, in our balanced equation we had N2 plus 3H2 producing 2NH3. The change in number of moles then is going to be 2 minus 4, so negative 2. That means that our delta N is negative 2, our negative N is 2. So negative 2 is delta N, positive 2 is negative delta N. If I look at the two equations up top, where I have a positive 2, that would be the same thing as a negative delta N. Where I have a negative 2, that's the same thing as a positive delta N. Substituting our delta N then, we wind up with the final generic equation such that the Kc is Kp times RT to the negative delta N, and Kp is Kc times RT to the positive delta N. I can apply this to that example that we looked at with the Haber process, remembering that the Kp value is 7.11 times 10 to the negative 5 at 500 degrees Celsius. So for this then, if I plug in this equation a delta N of negative 2, I'm looking for Kc from Kp, so I'm going to use the first equation. Plugging in the values, I get a Kc value of equal to 7.11 times 10 to the negative 5, multiplied by the gas constant R, 0.0821, multiplied by temperature, 773, which is our 500 Kelvin, or 500 Celsius converted to Kelvin, all raised to the negative delta N. If delta N is negative 2, the negative of that is going to be positive 2. When I multiply this out, I should get a Kc value at 500 degrees Celsius of 0.286.